Today's lesson is about solubility and using Table G. Now, there's a couple of things to mention first. Yesterday, or the last lesson, we learned Table F. Table F tells you if something can dissolve in water or not. That's it, yes or no, and that's the only thing it will tell you. Table G is going to tell you if something dissolves in water, how much and at what temperature. Because temperature obviously will affect things. We'll get into that in a second. First thing we need to do is talk about some basic vocabulary. So the term solution is what we would call a homogeneous mixture. Now the reason we call it that is simple. To be a solution, something has to be dissolved in water completely. Therefore, you're not going to be able to see different parts of it. That's what makes it homogeneous, and then that's why we call it a mixture, like salt water. So we're not talking about salt that hasn't dissolved. We're talking about salt that has fully dissolved and it looks totally clear like a glass of regular water. Now, the next set of vocab words are going to be the most important. Saturated, unsaturated, and supersaturated. Now, saturated, unsaturated are the ones we use the most. You may have heard of it. The term saturated fat and unsaturated fat, it means the same thing. It's just applied to a different part of chemistry. We talked about that in organic, but now we're going to do it here. So a saturated solution means that you are at the maximum. So what we're talking about is the maximum amount of material. I'm using the term stuff. If it were saturated, would be at the maximum amount that can be dissolved for that temperature and amount of water. We would call this a concentrated solution because you're at the maximum, and there can be excess. So in other words, if I make sugar water, if I keep adding sugar to water and I keep dissolving it, eventually I will be at the maximum amount that the water can dissolve. That would be the saturation point, or we would call it saturated. If I add any extra, it's just going to sit at the bottom of the glass and not dissolve. That would be the excess. Now, an unsaturated solution means you have less than the maximum, or you're under the maximum amount that can dissolve. Okay, that would be called a dilute solution. Dilute just means it's not fully concentrated to the maximum level, and there's never going to be any excess. And the reason is simple. If I have less than what's capable of being dissolved, then any material that's in the glass, we're using the sugar water example again, will just dissolve eventually. Now, it doesn't have to dissolve immediately, but eventually it will dissolve. That's why we won't have excess, because any sugar that would be there would be in the water dissolved, not sitting at the bottom of the glass. Supersaturated. That means this is a special case. For some reason, you are above the maximum amount that can be dissolved. Now, not every chemical can do this. Some chemicals don't. And they are obviously, I would go as far as to say they are super concentrated because they're holding more than what should be possible. Now, these solutions typically tend to be unstable. So if they are disturbed at all, if you add any extra material, if you shake them, if you stir them, they have a tendency to take all the extra stuff that shouldn't be able to dissolve will typically come out of solution as a precipitate. It'll fall out of solution as a precipitate and then become excess, and you'll end up with just a regular saturated solution. In other words, the real maximum will be maintained, but all the extra stuff will just fall out and sit at the bottom of the glass. We will learn that in a couple more lessons, more about precipitates. Now, there are some factors that affect solubility, and we have to worry about temperatures and gases. We'll focus on temperatures first because they make the most sense. Turns out, if you have hot water, so if you increase the temperature, it will be able to dissolve more stuff than cold water. So the relationship is direct. So as the temperature goes up, the ability of water to dissolve stuff increases. As the temperature goes down, the ability of water to dissolve stuff decreases. And the reason is simple. Hot water has more energy, so it can lift more things, whereas cold water has less energy, so it can't pick up as much. That's pretty much it. Now, as far as pressure doesn't affect it because it's a liquid and the molecules are so close together that pressure, we're talking about liquids and solids, so pressure is not going to have any effect on them. Gases. They do the exact opposite of solids. And there's a reason for that, and I'll explain it. So gases' relationship are indirect. As the temperature goes up, the solubility of the gas goes down, and the reverse is also true. Think of it like a rock skipping along a water surface. Everyone's seen this. So if I've got some body of water and I take a little rock and I throw it, it will skip, skip, skip. Eventually you'll start slowing down and then it will sink in. Okay? That's the general idea. Now, the reason I use this example is because gas molecules are moving, they're moving very fast. And so they essentially are the rock, and they don't slow down over time. So therefore, they'll just keep skipping and skipping and skipping, and they'll never actually fall into the water. That's why if you want to increase the solubility of a gas, you have to decrease the temperature. And the reason is simple. By decreasing the temperature, we slow down the gas molecules, and if we slow them down enough, just like the rock skipping along the surface, eventually it slows down enough, and then it goes into the water. That's essentially the same exact thing that happens with gas molecules. That's why they have an indirect relationship. Now, pressure is different. Their relationship with pressure is direct, and it's actually pretty easy. The gas molecules are skipping along the surface of the water. Well, if you increase the pressure, you're effectively pushing them into the water. So by increasing the pressure, you increase their solubility by force. And if you decrease the pressure, you decrease the solubility. An example is a soda bottle. If you take a unopened soda bottle, like a 2-liter bottle, and crack the seal, you start to see bubbling. That's because you reduce the pressure, therefore you reduce the solubility of the gas, so the gas can no longer stay dissolved in the liquid and it bubbles out. If you put the cap back on nice and tight, the pressure will eventually go back up. Therefore, the solubility of the gas will go back up, and the bottle will stop bubbling. Back page. Okay, factors that do not affect solubility. So, volume, stirring, and surface area. They're going to have no effect. They do have some effect, but not on solubility, not what you would think. So, volume. If you double the amount of water, you will double the amount of material the water can dissolve. But you didn't change the amount per unit. So in other words, 1 liter of water can dissolve, 2 liters of water can dissolve twice as much sugar as 1 liter of water, but they can't dissolve any more per liter. That's what solubility really is. It's a per unit issue. Stirring and surface area, same idea. They have no effect on solubility. If I'm dissolving sugar in water and I stir it, it will dissolve faster, but it won't affect the total amount that can dissolve. Same with surface area. Powdered sugar will dissolve faster than cubed sugar, but it won't actually change the amount that can dissolve in the long run. Like, you'll still have the same maximum amount. And this brings us to Table G. So Table G looks like this down here, and it actually has a bunch of different chemicals. And on the x-axis, we have temperature. On the y-axis, we have solubility in 100 grams of water. That's very important, because if I change the amount of water, I'll change the amount that can dissolve. That's basically this kind of idea up here. And so let's do some examples. So I'm going to look at KNO3 as the example chemical. So it's this line right here in yellow. And at any given temperature, as you can see, as the temperature changes, the solubility of KNO3 will increase as the temperature goes up. That's pretty standard. If you look, they all do it, but they don't all do it at the same rate. Now, there are a couple examples of ones that do the opposite. These 3 right here. Okay, they actually their lines go down as temperature goes up, and we can make the safe assumption, since they do the opposite thing of everybody else, they're going to be gases. And that's because gases, their solubility is inverse to temperature, whereas solids are not. So that's pretty much it. And again, you can see even NaCl slowly goes up a little bit. Now, I have 3 points I want to mention. So if you are given an amount that hits the KNO3 line, let's say, like this would be about 105 grams of KNO3 dissolved in 100 grams of water at 60 C, I'd be on the line. That would be saturated for that temperature and that amount. If I change the amount or if I change the temperature, then all bets are off and I have to check it again. So if I'm on the line, I am saturated. If I was given an amount like 120 grams at 60 C, that would put me at some point above the line. well, that would be supersaturated. And if I was at 90 grams, let's say, or really anything under 105, but if I was at 90 grams and 60 C, I'd be under the line, so then I would be unsaturated. If I wanted to saturate that solution, I would have to add the amount needed to get up to the line. If I was supersaturated and I disturbed it in any way, then the amount that would fall out would be the amount that it takes to get me down to the line. And that's pretty much how Table G works. I'm going to post a second video doing some practice problems from our Table G worksheet.